Good morning, everyone. I'm Rodrigo Nascimento from the University of São Paulo. Today, I'm going to present our paper entitled Advanced Control for Petroleum Pipelines, Part 1, Equivalent Electric Dynamic Modeling. This work lays the foundation for designing adaptive and robust controllers, modeling long-distance oil pipelines using an analog circuit-based approach. Pipelines play a central role in ensuring energy delivery to society. They transport large volumes of fuel over long distances, often across remote terrain. These systems face several operational risks. Pressure surges and cavitation may lead to structural failures, causing leaks that can affect the environment, local communities, and company image. To ground this discussion in a real-world context, our study focuses on a multi-product pipeline that transports gasoline and diesel. The figure shows fuel station facilities connected by a 37-kilometer line crossing varied terrain. The main challenges are the strong nonlinearities in flow dynamics, significant uncertainties in fluid viscosity and specific mass, and risks of cavitation and pressure surges during operation. Accurate modeling is essential for designing the control system. In practical control design, two paths are typically followed: direct system identification through physical testing, or model-based synthesis. However, field testing pipeline dynamics is logistically complex, operationally risky, and resource intensive. To minimize plant interventions during controller design, a high-fidelity simulation model offers a practical alternative to reduce operational impacts. Our objective is to develop a control-oriented equivalent electric model that captures both transient and steady state of pressure and flow dynamics. This model serves as the foundation for synthesizing advanced control strategies in future stages of our research. Let's now take a closer look at the pipeline's physical structure and control loops. At Station A, on the left, booster and main pumps supply the pipeline through a pressure control loop. A second loop, with the same purpose, located at Station B, on the right, prevents gradual pipeline damage. Both control loops are designed to avoid overpressure and cavitation. Below, you can see the hydraulic schematic that illustrates these control stations. Here, on the left, we revisit the same hydraulic schematic, and on the right, we show its simplified electrical equivalent. This forms the basis for our modeling approach using the classical hydraulic-electric analogy. In this analogy, pressure corresponds to voltage, flow to current, frictional losses to resistances, fluid inertia to inductances, and fluid compressibility. The bulk modulus maps into capacitances. This modular representation provides an intuitive basis for analysis and implementation in general-purpose computational platforms. Moving on to the component level, each pump is modeled as an RLC branch to capture dynamic head flow characteristics. To extend the model's applicability to viscous fluids, we integrated empirical correction factors originally developed for single-stage pumps. In this work, we adapt those equations to multi-stage pumps by scaling the correction factors according to the number of stages. This mirrors a series association of voltage sources. The figure shows the curve adaptation points illustrating how viscous effects distort pump performance. With this correction, the model remains accurate across a wide operating range, supporting realistic dynamic simulation and control design. In addition to improving pump modeling through viscous correction, a central advancement in this approach is how we formulate hydraulic capacitance. Traditional pipeline models usually compute hydraulic capacitance based only on fluid compressibility, expressed by the bulk modulus. However, this simplification neglects the elastic behavior of the pipe wall, the Young modulus, which becomes significant in long-distance pressurized systems where dynamic pressure waves propagate throughout the pipe. Our main contribution is the analytical inclusion of pipe elasticity into the classical capacitance model. Using principles from mechanics of materials and applied elasticity, we derive the pipe wall expansion and integrate it with the fluid compression term. The resulting expression combines both effects. The first term, involving the pipe's mechanical properties, accounts for wall elasticity, and the second term, involving fluid volume and bulk modulus, reflects fluid compressibility. This correction enhances the model's ability to capture transient effects such as pressure surges and wave reflections, phenomena that directly affect pipeline control system performance. As a result, this formulation enables accurate simulation of hydraulic dynamics without relying on physical testing. We now turn to how the system is numerically solved. The computational method applied was the finite difference method as depicted in the diagram on the left. To ensure numerical stability and accuracy, we conducted a parametric evaluation shown in the chart at the top right, comparing computation stability with multiple mesh configurations. This analysis led to an optimized discretization strategy that balances accuracy and the simulation time. The trade-off plot at the bottom right highlights the balance between performance and computational cost. The solution performance, shown by the green curve, improves with finer subdivisions up to 240, but deteriorates afterward due to truncation effects. Meanwhile, computational effort, shown in blue and plotted with inverse normalization, increases steadily with mesh density. The optimal configuration, indicated by the red trace, was set to 230 pipeline subsections, represented by RLC meshes. For our model validation, the first step was carried out using real historical data collected from the physical plant. The plots at the top of the slide show pressure readings of the pumps, comparing the electric model simulation with measured data. At the bottom left, we present pressure and flow at the pipeline ends. Again, the model shows close agreement with the physical measurements. On the right, the steady state percentage deviations are summarized. All results remain below 2.5%. This demonstrates that even with only one operating scenario, the model reproduces steady state pressure and flow behavior with high accuracy, confirming its potential to support advanced control design. We then validated the electric model against a widely used industry-grade pipeline simulator, which is safety-oriented and commonly applied to mechanical design. It was used as a benchmark across 6 operating scenarios. These scenarios, shown in the table, include variations in fluid properties and flow rates. The plots compare the flow responses, and the bar chart displays the percentage deviations. Across all cases, the mean absolute percentage error was 3.2%, with all but one case staying below 5%. These results confirm that our model aligns closely with the reference simulator, establishing a robust foundation for the dynamic tests that follow. In this final calibration step, the model was subjected to more severe transient scenarios, including pump shutdown followed by valve closure at both pipeline ends. The upper plots show the pressure transient at station B. We observe good agreement in the oscillation period, as shown in the absolute values bar graph left below. However, this graph also shows a divergence in the amplitude as discussed in the paper. Interestingly, both models show this deviation when compared with theoretical calculations. The chart on the right shows that the root squared error relative to theoretical results is similar for both approaches. This suggests that the discrepancy is not model specific, but rather stems from discretization limitations common to hydraulic solvers. In conclusion, we presented a refined capacitance formulation that incorporates pipeline elasticity, allowing the model to capture system dynamics in both steady and unsteady states. We also adapted viscous correction factors to represent multi-stage pump behavior, extending the model's applicability to heavier fluids. The discretization strategy ensured numerical stability and avoided spurious resonance peaks, enabling accurate and reliable simulations suitable for control development. The model was validated through a structured methodology involving real plant data and a benchmark simulator. Looking ahead, Part 2 will explore the limitations of classical PID controllers in oil pipelines. Part 3 will investigate adaptive multivariable control, and Part 4 will address robust observer-based strategies. I'd like to express my gratitude to the Polytechnic School of the University of São Paulo, to CAPES for supporting this research, and to the conference organizers for the opportunity to present. If you have any questions or would like to discuss the work further, feel free to contact me by email. Thank you once again for your interest.